reasoning, yes or no, for each letter. And then turn your homework to page 2. That's where I'll stamp your notes. Hopefully everyone did them. If you didn't do them, you might find today's worksheet a little bit difficult. We are working in groups. So if you didn't do the notes, do them ASAP. And then get help from your group today to figure out how to do it. So really, really good addition. So you do need a force to get an object at rest moving, right? So if you're in outer space and you're an astronaut pushing the box, if you want the box to move, you need to apply a force. But once that box is moving, a force is no longer applied. Is it going to continue moving forever? What did we say last class? Yes. So this question states, if there is motion, a force is acting on it. Once the box is moving, it'll continue moving forever, theoretically, and no force is acting on it anymore. So after the force is applied, you've got constant motion forever. So this one is a common misconception. The answer here is no, because even though you started with a force, it's no longer needed to keep it moving. Does that make sense?
We got it.
You want to change it, yeah. And because you want to make sure you correct that misconception. And this is something that is common in the unit test. So I always try to test you on some of those common misconceptions. Very good. So go ahead and we're going to jump to H. And this one is the stronger the force, the faster an object moves.
So we said the answer that you said that was false because how fast an object doesn't only depend on the force. Because even if you change your force from even if you double it, but you're trying to push a 20-ton rock, it's not going to change.
Beautiful.
So it's not the only amount that matters in this scenario.
There's lots of factors. Good. This one is no, and I love their reasoning. Force will accelerate an object, but it also depends on other factors like the mass and the inertia of the object. So I can push this box with very little force, but I try to push this table. It takes a lot more force, and it's accelerating much more slowly. What if I tried to push the wall? Am I going to accelerate it? Even if I was like crazy strong, am I going to accelerate that wall? Even with tons and tons and tons of force? No. So force for H does not necessarily determine how fast an object moves. You can apply a lot of force and it doesn't move at all. Just like the boulder example. Question?
Is it okay if I said yes? Because I was assuming there's only one object involved. Like, I was assuming that, like, you push one object, but you push the same object with the software force of its faster. That's all I.
So, that also comes back to, it depends on the object, right? Because the wall, I can push it with a little force, and it doesn't accelerate. If I increase the force, it still doesn't accelerate. So, because it wasn't specific, you want to make sure to think about it in broad terms.
But if you push the wall, it wouldn't be an external outside force, because before you're just going to the wall, so you're not really outside force. You're internal.
So when you're thinking about, and we didn't get too deeply into this, we talked a little bit about balanced forces, right? So the wall by itself, it's definitely got gravity, it's got the force of the floor, it's got the force of the wall behind it. Everything is balanced at this point just because everything's balanced because there's no motion. My outside force doesn't move anything, but you want to think about it in terms of, I get where the confusion is, but you want to think about it in terms of an applied force, meaning someone or something pushing it with a variable type of force, if that makes sense. Any other questions? Answer for H is no. Let's go on to B and I. So we'll start with B in group number 7.
Okay, so B, if there's no motion, then there's no force acting. B said false. Because if there's no motion, then that just means that force is here, but there can still be other forces.
Good. So if I have this box sitting here, there is gravity acting on it. There's always gravity acting on an object on Earth, but there's also the force of the table. So there are forces acting on it. They're just balancing each other out so nothing is moving. Any questions on B? Perfect. Then let's go to I. I is constant speed results from constant force.
You also said false for this. Constant force would result in acceleration. However, two opposing constant forces, such as pushing it, both constant pushing, constant friction, can result in constant friction.
Good. When we talk about constant force here, we usually think about it in terms of unbalanced force.
Okay.
But really good interpretation of the question and think about all the different scenarios. Beautiful. So false and false for B and I. Any questions on I? Let's move on to 6. We've got C and J. So let's start with C.
You said no because there can't be a force without motion, and when you push down on the table, the force of your hand and the force of the table are able to push it.
There cannot be a force without motion. No, because you can have a force on the table and there's still no motion. Great. Perfect. Do you guys agree? I can apply force and still no motion? Let's move on to the next one, which is, what was it? Jay?
Yeah, a force is necessary in order to change the direction of motion. We said yes because there's no way to change directions without another force. An example, if an object is rolling forward and it goes down a 180-degree spiral ramp, it's changing directions, but it's not changing direction of motion. It's still rolling forward. If it hits a wall and rolls the other way, that's changing direction of motion.
So this one is the true statement. In order to change a direction of motion, you need a force. It ties back to the second law that an outside force or an unbalanced force creates acceleration, and slowing something down to change its direction is a type of acceleration. A lot of students think if I'm accelerating, I'm only speeding up. But in physics and science, acceleration means any change in speed, which is change in direction, speeding up and slowing down. So J is yes. I think that's the first yes we have, the first true, right? Let's move on to group number 4. We've got, is it D?
Yes.
Okay.
So we said that it's true because if an object is in an environment without friction or any other like opposing forces, it will pretty much move indefinitely without the help of more forces.
This is the idea of the object in space, right? An object can continue moving in a straight line without applying a force. So a lot of students think that you need a force because we have friction here on Earth or air resistance, but in space you don't need it. So D is our second true statement. Any questions on D? Okay, let's move on to K. Forces makes things go, losing energy makes them stop. Okay, so this group, remember the idea of kinetic energy. Kinetic energy is motion. Kinetic energy is also related to friction, kinetic friction. But one thing that I didn't teach you yet about energy, and you might have learned this when you did your Goldberg machines. Can energy run out? No. Energy cannot run out. So that term, runs out, makes this statement false. So K is false. Energy cannot run out. Question. Oh, so the Rube Goldberg machine is something that I think a lot of students did in middle school. No?
We were gonna do it, but COVID hit.
Oh no, you guys never did it. Oh, okay. I'll show you a video. There's an activity where you build this contraption that shows how an object can move from one place to another to develop sort of an action. I can pull up videos for you toward the end of the period. I'll show you what a Rube Goldberg machine is. Thank you for reminding me. I didn't even think about that. Maybe we'll do it in this class since you didn't get to do it. I love that project. Yay! Okay. Let's move on to group number 3.
Okay, so we had an email, for E, we said false. And we said, for example, in our space, you push an object, it will continue constant motion, even without constant force. So if you push lots of
Good. Be kind of question. Yeah. Can you get to the Okay, so this one was kind of something we've already talked about, right? An object is moving. There doesn't have to be a force acting on it, very similar to A, if we were in outer space and there was no friction. Any questions on E? And then L is the last one. Force can be transferred from one object to another during motion. So this one, I haven't taught you yet. This is stating that force is a property of the puck and that force can transfer. Tomer, did you want to add to it?
It's kinetic energy transferring through that.
So it's not force that's transferring, it's energy that's transferring. So L is actually false because you can't transfer forces. It's actually the energy from the puck that's transferring in your example. What is happening is in your example here, the hockey puck had a force applied to it, maybe by the hockey stick. And then when it hits something, it's applying the force from the puck onto the new object. So forces are applied, they are never transferred. Energy is what's transferred here. So good addition, Tomer. Let's move on to 2. So you guys did which question? F. And they only had one question, so we're almost done.
and have moving objects up when their parts moving down. So if you push an object based on going forever.
Beautiful. Can you ever use up a force? There's no such thing as using up a force. You apply forces, but you never use them up. And that example is exactly perfect. If I was in outer space in a vacuum, then that push would, or that constant motion would be forever. Let's go on. And were there any questions on that? Group number 1. You guys did G, right? Okay.
Okay, so we said yes and no.
Okay. So let's read the question first.
Oh. Okay.
So forces act on objects at rest.
Yeah, we said yes because objects say like on Earth. At rest has Earth's gravity acting on it.
Very good. Just like this box.
Yeah, but then no, it's a perfect space, like without any obstruction. There are no forces, so an object that rests.
So if you're thinking kind of globally, let me look at the question. Forces act on objects at rest. If you think about things globally, you can have that scenario be true, but it's not always true. Exactly like you said in part A, you can have balanced forces like gravity and the force of the table to keep it at rest. So there are scenarios where G is true, but we want to think Is it always true? And it's not always true, so that would be false.
So you say it was in space, you need
If it had a force applied to it. If it was kept at rest, I know it's hard to believe, but if it was kept at rest, it would actually never move, as long as no outside forces were acting upon it. Is it Jake?
Yeah. Just like G, right?
What?
Not like G.
Yes.
Well, good and all interacting on like
But the answer is yes. Yeah. So G would be forces act on objects. Sorry. Did I say false?
yeah.
This is true. G is true. Sorry. G is true. My bad. G is true. Okay. Any questions on the warm up? This was like a brain blender. We're going to go into our worksheet 1. So I want you to pull up your packet and turn it to page 3. Yes, I'll put it. No worries. Go ahead and you're putting your whiteboard aside for now, and you're just working on this worksheet within your groups. For those of you who did not do the note, I want to make sure that you consult your group members as to how to do this assignment. Oh, they returned. Did you have the did you take the glasses off?
Yeah.
No, someone must have taken it. You know what? Go ahead and go. I think you were next in line. Let me print it out for you guys because I don't want to waste any packets. So I can do that now.
Yeah.
Slide over.
Challenge. Let's use the pencil and work on it. Who else? Anyone else who wants to do the worksheet? If you can hear me, clap once. If you can hear me, clap twice. Remember in Miss Lee's video, for those of you who saw it, she emphasized a lot of the little details that are important for drawing force body diagrams. Remember? I will be giving you a quiz, and I will be grading all those teeny tiny details. Did you label the axis, X and Y? Did you draw the dots in the center? Did you label your forces appropriately? Those are the things I'm looking for. And a lot of the information that was in that video, I put it into, let me pull it up here, a little slideshow. So unit slides, I don't think they're accessible to you till the end of the period, or sorry, the end of the school day. But you can see, let me scroll down to the appropriate slide. You can see a lot of the things that Miss Lee discussed in her video. So it talks about what is a force. It's a push or a pull. It talks about the types of forces, contact, versus long range. And it talks about friction, which is a contact force that opposes motion. So we've got surface friction, like sliding across a surface, or air resistance, which is friction from the air particles. And then we've got these special vocab words called normal, which is the upward force of the floor or the ground or the table. And we've got tension. Gravity, I forgot to put this in. Let me add it in right now. Gravity is really the force of the earth. So anytime you talk about forces applying on an object, you always want to discuss what that object is that's applying force. So instead of saying force of gravity, you're going to call it force of earth on the box, or force of earth on the person, for example. So I always want to make sure you discuss force of something on something. Does that make sense for those of you who watch the video? Okay, go ahead and get into your groups. Do your very, very best. Try to help out your group members if they haven't seen the video yet. And then those of you who haven't seen the video yet, make sure you do it this weekend before we take our test. These little swish marks, I call them swish marks. If they are equal, what does that mean? What does the swish marks mean if they're equally spaced? Constant speed. If they are getting smaller and smaller, what do you think that means? It's getting slower and slower. And then if it's getting wider and wider, it's speeding up. So that's what those swish marks mean. I had a good question about question number 5. They don't tell you what this force is that's pulling it forward. If you don't know what the force is, we generally call it an applied force. You can also call it a person if it doesn't specify. But if you don't know, I generally say applied force, or FFA on box. But what I'm going to do instead is I am going to have you, if you didn't finish it first and correct it using the answer key. So we have a video answer key up here, and I'm actually going to post like the paper copy. If you don't want to go through the whole video and you just need specific answers to check your answer, then that'll be fine. If you have any questions, you want to make sure to reach out to me. I'm going to have one practice problem for our warm-up next class, and I'll answer any questions you have on that. And then we're going to do a quiz on this. So this is key for the students that did not take the notes from last night or from the previous class. Please make sure to do that. It's very important because there are a lot of little details on your quiz that I'm going to ask you to put down. And if you don't do those little details, you are going to get docked points. The second thing I want to talk about is your homework for tonight is on a program called Physics Classroom. And you need to create an account so that I can see your score through that website. So what you're going to do is you're going to go into physicsclassroom.com. You're going to open this document, and you want to make sure to use your Los Gatos email to log in. And then you're going to use the course code ANHIRE 2022. That's how I can see whether you completed these assignments or not. If you complete them late, that's okay, but you have to email me because it's not like Canvas where your assignment pops up and says, make sure you grade this was turned in late. I'm not going to get an alert from Physics Classroom telling me that students did their homework late, so send me an email and then I'll update your score. So this is basically the exact same thing as what we've been doing in class. Miss Lee put together a video. If you are struggling, this video is going to help you do this this activity successfully. But basically, in this activity, they use a different form of writing out forces than I want you to do in class. So I'm just going to log in as a guest. You want to do both levels. We'll jump into the wizard level first, and then you're going to read the description. A downward moving skydiver maneuvers into a spread eagle position and momentarily slows down. Here, you're going to click to get different diagrams. So I want you to notice they put force of gravity. When you do your test, I don't want you to say force of gravity. I want you to say what object is creating that force of gravity. What is it?
Earth.
Force of Earth on the skydiver. So don't write it out, just say F of E on S. Here they say force of air, and it should be force of A on S, skydiver. So you're going to see different scenarios. You're going to see symmetry marks. This one means that they're not equal. And if we're thinking about this scenario, what type of force body diagram should I be looking for? What is my contact force? Always think about what's in contact with the skydiver. Any thoughts? Tomer. Air. The air particles is a contact force. What about a long range force? Earth. That's your gravity. So what we're looking for is gravity and air. Should they be equal? Should I have symmetry lines? No, because it says slows down, meaning that it's not constant speed. So which one should be bigger?
Air.
Earth.
Air should be bigger. This is a tricky one. If it's slowing down, that means your larger force is pushing it up. And that's what causes it to slow down. Even though it's moving downward, it's the larger upward force that slows down that acceleration. So we've got double lines, meaning that's longer than the gravity, and you're looking for that data wave symbol when you submit your answer. If you miss it, you're going to have extra practice problems on that same concept. Students get really frustrated with concept builders because if they mess it up, they have to do it a couple more times over and over and over again. This is where students say, oh, I've been spending hours on this assignment when it really should only take me about maybe 15, 20 minutes, maybe 30. If you are spending more than 30 minutes on this assignment, come and see me during tutorial. Do we have tutorial next week? Okay. So come and see me during tutorial. Okay? So your homework tonight, we're not gonna, we didn't do the whiteboarding, but I want you to check your answers. So you're checking your answers at home. You're contacting me or coming to see me during tutorial if you're confused. You're doing this homework after you've created an account with my ID. You're finishing Newton's first law. I actually saw some students already submit it, which is awesome. So finish Newton's first law and then study for that quiz. Quizzes only worth 10%. So do your best. And if you don't do well, you can always retake it for 70% score. Oh, the other thing I wanted to mention is I did post, you might get an announcement in your email. I did post an example CER. It's on a different claim, but for those students, it's right here. I'm going to attach it to today's page. For the students who want to see what a 100% CER looks like, you have an example to reference. This one is not focused on Newton's first law. It's more focused on mass, and how the greater the mass, the greater the inertia. So greater its resistance to motion, or greater its resistance to stopping. So I did pull in lab stations from our Newton's first law lab, and it's a really good reference when you submit your CER question.
How do you want format?
I'm not a stickler. I'm not an English teacher, so I'm not a stickler about making it like MLA or whatever format that you're used to doing in English. I'm really looking to see if you got the physics concept right, and if there's a lot of careless mistakes. I know a lot of students are used to shortening words or abbreviating things.
Good morning, Bobcats. Just a reminder that this is your last planned tutorial. All students need to go to their 5th period class for tutorial today. Staff, there is a video link that has been emailed to you this morning. And please make sure you keep your students all the way until the bell rings at the end of tutorial. Happy Friday.